Hey everyone, we're going to come back with more stats today. And before we get too far into chapter 9, we're going to actually look at things that could go wrong with your hypothesis tests. So let's take a look. What could possibly go wrong? So, Wolverine Worldwide, a shoe company in Rockford, improperly disposed of chemicals, PFASs, which have leaked into the groundwater. Whoa, too close to home on that one for some people, I guess. The state's drinking water limit is 70 parts per trillion is considered to be safe. So 70 parts of PFAS per trillion is considered safe. Anything above 70 parts per trillion is dangerous, and officials believe that the Rockford water is unsafe, or it might be unsafe. So they take a random sample of 200 households in Rockford, and they find the average lead level to be 70.5. Ooh, that's scary because that's above the safe limit. But does that mean for every household in Rockford, the average is 70.5? That could be just for those households that we sampled. And we would say that we just happened to take a sample of 200 households that all had higher than normal levels of PFAS. So we're going to start by stating hypotheses. And before we do that, I want to make sure that we noticed that we took an average lead level. So when I see that, or when I saw that, my immediate thought is we're going to be looking at mu and not p. Start off by writing the appropriate hypotheses for performing a significance test using words and symbols. The first thing to do here is to define, well, what is our mu? What is our population average? With all of AP statistics, if you're going to use a symbol, you have to tell the reader what that symbol is standing for. So I can't just use mu without writing someplace that mu is the average PFAS level in Rockford drinking water. Now there are a lot of numbers here, and the first one that is concerning to me is that 70.5, and that 70.5 came from a sample. So that 70.5 can't be the null value because it comes from the sample. The only other number that I see here is 70, and that's kind of, we should have gone there right away maybe, because that's the break point of the PFAS. Either it's greater than 70 or it's less than 70. So that's going to be our null value. Great. So we have our hypotheses. Again, notice that it is the same number in H naught as you see in HA. It always has to be the same number. After conducting a significance test, a p-value of 0.45 is found. Let's interpret that value. We'll start with our sentence frame, and we'll go and fill in the blanks. So H naught in context. P-value is 0.45. Sample size was, where is it? 200 households. Parameter is mean because, mu. And then notice that our alternative hypothesis is greater than. So whatever our alternative hypothesis says, that's the one we're going to choose here. So mu greater than, because alternative hypothesis is greater than. And then the statistical value is at 70.5. That's what came from our sample. And then we're going to adjust for readability. If the average PFAS level is 70 parts per trillion is true, okay, I don't think I need the is true, there is a 0.045 probability of a sample of size 200 households having a mu greater than 70.5 parts per trillion. Okay, that reads pretty good. Based on the p-value, should Rockford keep the current water or switch to bottled water? Well, the p-value is less than our typical alpha, and our typical alpha is 0.05. So to answer this a little bit further, I'm going to go ahead and just grab the sentence frame for the conclusion. And since the p-value is less than alpha, the data supports that the average PFAS level is greater than 70 parts per trillion. And if the average is greater than 70 parts per trillion, then Rockford should switch to bottled water. Now let's suppose that the decision is wrong. What's the consequence of that error? Well, I think what would happen here is that we've just told an entire community that they have to drink bottled water at their own expense, probably, and there was no reason for it. And given that the water is safe, how often is this going to occur? So remember that the hypothesis test presumes that the null hypothesis is true. In other words, in this case, it's going to assume that the water is going to be safe, or that the PFAS level was 70. And if it was PF 70, that means that we told through our alpha level that we're going to reject the null hypothesis at the 5% level. So the probability that this is going to happen is 5%. So since alpha is 0.05, this error is going to happen 5% of the time when we presume that H naught is true. Now let's suppose that the p-value is 0.14. Should the town keep the current water or switch to bottled water? To answer that, we'll go right back to our conclusion of a hypothesis test. And we get, since the p-value is greater than alpha, the data does not support that the average PFAS level is greater than 70 parts per million. If we're greater than alpha, we do not support the alternative hypothesis. So Rockford should not switch to bottled water. Now here's a nightmare situation. Let's suppose that that decision was wrong. What's going to be the consequence of that? We've told a lot of people to switch to bottled water, and that was the wrong decision. So the water is contaminated, and we told people to drink the contaminated water. So sickness and death are probably going to be the consequences. So which of those two consequences is more serious? I would think number 7 is the more serious. Yeah, number 7 is more serious because getting sick is a much more serious consequence than just wasting your money. And let's face it, in today's climate, most people are going to be buying the bottled water. If there's even a hint that the water is unsafe, people are going to be switching voluntarily to bottled water. So we just took a look at the two different kinds of things that could go wrong if we make a bad decision on our hypothesis test. Now in the first one, number 4 and number 3, we're saying that the null hypothesis was actually true, but we made a mistake and told people that the alternative hypothesis is true. In a type 1 error, H naught is true, but we mistakenly conclude that HA is true. And then the opposite situation, that's a type 2 error. And in a type 2 error, HA is true, but we mistakenly conclude that H naught is true. Now, depending on circumstances, either the type 1 error is more serious or the type 2 error is more serious. And a thorough studying of stats means that you have to look at the consequences of making these two different types of errors, and you try to minimize the probability of making the more serious error. So if I think type 1 error is more serious, I'm going to decrease the probability of making a type 1 error. And if I think a type 2 error is more serious, I'm going to decrease the probability of making a type 2 error. Or at least I'm going to try to decrease the probability of making those two errors. And that should kind of make sense, but unless we actually talk about what the different kinds of errors are, then we wouldn't really have a way to discuss this intellectually. So let's move on to our important ideas. And the first important idea is about that type 1 error. And in the type 1 error, we think that the null hypothesis is true, or the null hypothesis is actually true, but we make the wrong decision. So we conclude that the alternative hypothesis is true. For the type 1 error, we actually know the probability that that's going to be true, and that's alpha. So by making alpha small, we can minimize the probability of making a type 1 error. So small would mean that alpha is equal to 0.01. Now in a type 2 error, the alternative hypothesis is really true, but again, we're going to make the wrong decision. We're going to say that the null hypothesis is true. Now the probability that this occurs is called beta. Now the probability that a type 2 error occurs is going to be given by a probability called beta percentage of the time. Now we're not really going to take a lot of time to calculate beta, and it's not really necessary for us to in the scope of the AP stats, but you do need to be familiar with the vocabulary. Beta is the probability of making a type 2 error. So we said that you can control the probability of making a type 1 error to some degree by using different types of alphas. So what I generally tell my students is that if type 1 error is more serious than the type 2 error, then you want to make your alpha equal to 0.01. If the type 2 error is more serious than the type 1 error, then you want to make your alpha bigger than that. You want to make your alpha 0.1. And then if you want it to be balanced, then that's when you would use an alpha equal to 0.05. So those different alpha levels are all, they are a part of error analysis, or a big reason why you pick them is because you want to be able to control the risk of being incorrect. Moving on to our check your understanding, we've got the manager of a fast food restaurant wants to reduce the proportion of drive-through customers who wait longer than 2 minutes to receive their food after placing an order. Based on store records, the proportion of customers who have to wait longer than 2 minutes is P equals 0.63. To reduce this proportion, the manager assigns an additional employee to drive through orders. During the next month, the manager collects a random sample of 250 drive-through times and finds that P hat is equal to 0.576. The manager then performs a test of the following hypotheses at the 0.1 significance level. So P is equal to 0.63, which would be the historical wait time, and P is less than 0.63, which signifies that he's reduced the wait time. Where P is a true proportion of drive-through customers who have to wait longer than 2 minutes. So first of all, let's describe a type 1 and type 2 error. In a type 1 error, the null hypothesis is actually true. So 63% of customers wait 2 minutes or more in reality. So the manager makes the mistake of thinking that the proportion is actually less than 63%. So in a type 1 error, the null hypothesis is actually true, but we believe the alternative hypothesis. In a type 2 error, it's the exact opposite. The alternative hypothesis is actually true, but the manager makes a mistake and thinks that it is actually 63% or more. Okay, so review, type 1 error. The null hypothesis is actually true, but we're going to believe that the alternative hypothesis is true, and that's a mistake. Type 2, we think the alternative hypothesis is true, but in actuality, the null hypothesis is true. No, wait, that's backwards. In a type 2 error, the alternative hypothesis is actually true, but we mistakenly believe that the null hypothesis is true. So type 1, null hypothesis is actually true. Type 2, alternative hypothesis is actually true. So which of those two errors is more serious in this case? And you may or may not have differing opinions on this. But from the managerial point of view, I think the type 1 error is more serious. In the type 1 error, the manager thinks the extra employee that he's paying for is decreasing that wait time, but it's not. So from the manager point of view, you're wasting your money here with the type 1 error. Based on the answer to question 2, do you agree with the company's choice of alpha equal 0.1? Why or why not? And I think we had a great discussion of that already. If we think the type 1 error is more serious, then we needed to use an alpha of 0.01. So this was actually a bad choice. So if the null hypothesis is true, then the manager is going to make the wrong decision about 10% of the time over the long run. If the type 1 error is more serious, then you really should be using a smaller alpha level, maybe a 0.05 or a 0.01. The p-value of the manager's test is 0.0385, and interpret this p-value. So we're going to copy and paste our sentence frame, and we're going to fill in the values. So if the proportion of wait times is greater than 2 minutes is actually 63%, then there is a 3.85% probability that a sample of 250 drive-through times will have a proportion at most 0.756. So that kind of does it for our Stats Medic today, and we'll see you guys next time when we look more specifically at, and I think the next one we're going to do is a significance test for proportions. So be excited for that. See you next time.